Welcome. I'm going to say a little bit about what C++ is, and in particular how it came about. There are some pictures on my slides to compensate for the fact that the rest is text and code, and all the pictures have something to do with C++. And one of the things that make me excited about programming, about system building and languages, is that it's used for so many interesting things. So there's a little Mars copter that succeeded spectacularly, and I was very pleased to know that the flight software on board was C++. And to go back in the beginning, I had a problem that I needed to solve. And I just started at Bell Labs in Murray Hill. The problem involved management of very significant complexity and direct manipulation of hardware. And there wasn't any language at the time that could really do both. So I had to build a tool for that, and that's where C++ came in. My ideas for that involved the C's ability to handle really low-level stuff like device drivers, process schedulers, and such, and Simula's extensible and strict type system. I worked with both of those languages, so I knew them reasonably well. What I didn't like about those languages and things that needed to be improved to create something more ideal was that C didn't really enforce its type system. Dennis Ritchie said that C was a strongly typed language that was weakly checked. And I felt we could do better than that. C was very good if you didn't make mistakes, but you could help with its catching of errors and with expressing ideas more directly as you could in Simula. Simula, on the other hand, treated types, built-in types and user-defined types very differently. So if you look at this, that was a notation for an object of a type that you had defined. And this was the way you could try that with a built-in type, and it didn't work. On the other hand, you couldn't do the built-in types syntax for user-defined types and vice versa. C, you could get really bad mistakes very simply, like square root of 2 led to a crash in those days because the compiler didn't remember what the argument type of square root was. And Simula's performance was not up to serious systems programming stuff. And both languages lacked parameterized types. You could write a vector of integers, you couldn't write a vector of t, where t was a parameter. And that set off a quest for doing things much better. I was looking for a way of simultaneously get expressive code, complete type and resource safety, and optimal performance. Getting one or two of those is not all that hard, but getting all three is, took a couple of decades. So basically, here's an example of what we can get in C++ today. I have a vector. It's parameterized by the argument type, the element type, so vector of doubles with some well-known doubles, and vector of strings with some well-known language designers. And you can go much further than simple data. Here is a thread, and I can make out a pair of strings and threads and build it up. And the important thing here is that C++ manages its resources based on constructors and destructors. Constructors initialize things, build things, destructors clean up anything there is. And in particular, all resources here are deleted right at the exit from the scope. So when you have direct expression of ideas, you can then have compilers help support it to be fast, and we can eliminate resource leaks. I knew from the beginning that there was no way for me to build an ideal language. It was not an academic exercise where you have a 10-year project and then you come up with perfection. First of all, you don't come up with perfection. You can't define what perfection means. And anyway, I didn't have a design, implementation, and marketing team. I had hardly any budget. On the other hand, I had a really great technical environment with great colleagues. You can see some of them on the picture. And we worked in that building there in Murray Hill in New Jersey. That's where the key software research for Bell Labs were. We got C, C++, we got Org, got Unix, all of that out of that building. And so I had to start small and grow. That's generally a good idea for any project. Get something that works and then expand based on feedback and real world use. And don't grow so fast that you're getting ahead of your feedback, getting ahead of your experience. You have to take it reasonably slowly. On the other hand, you can't grow, you can't move incrementally unless you have a pretty good idea of where you want to go. Otherwise, you just pile on features and hope it works. That's not a strategy. And you have to rely on articulated principles because that's the way you sort of semi-formalize what you're trying to do. And also, if you can't articulate principles, you get steamrolled by requests for doing things differently or doing more, or something like that. One thing I decided pretty early on, like the first couple of weeks, was I didn't want a specialized tool. I wanted something that could express solutions to a large set of problems. And so C++ is a tool for building complex systems that require efficient use of hardware. That is the formalization of the idea is from C and Simula. And if you want to look at language features rather than what its purpose is, then C++ is a general purpose language for the definition and use of lightweight abstractions. Lightweight abstractions are little things like points or complex numbers or assertions of various sorts. It can always be expressed directly. And so the key aim was to support resource-constrained applications and to support large-scale development. And over the years, C++ grew from, one user to currently more than 500,000. And the interesting thing here is that, there wasn't any budget. This was coming out of enthusiasts in various places with me and later the standards committee guiding it. And we're now getting pretty close to what I was dreaming about in the 80s with C++ 20 bringing back coroutines as I used them in the 80s and getting all kinds of new modern features that are good. Technically, we're still back to these two pillars, a direct map to hardware. Even unusual hardware, we can get to use signal processors, GPUs, FPGAs and such through packages and tools that you can access from C++, and zero overhead abstraction in production code. That is, it's not good enough just to be able to say something in the language precisely, directly. You also have to be able to afford running it on a computer that is affordable in the context. It can be the processor on the little Mars helicopter, or it can be in a turbine there where there's not shortage of power, or it can be a normal computer. So by zero overhead I mean that what you don't use, you don't pay for. There's no distributed fat in the system. And what you do use, a language feature or library, you shouldn't be able to hand code it any better. And we aren't perfect of that, but we've been pretty good over the years. You can always be more specific or write more efficient code when you need to. That can be hidden by an interface or something, but you have to be able to use the hardware well. So I make a claim sometimes that C++ is an invisible foundation of everything. Everything's obviously a bit of an exaggeration, but it's closer to the truth than a lot of people are willing to believe. Even systems without a line of C++ tend to depend on systems that are written in C++. And so every thing is a pretty good first approximation. Foundational uses of C++ is typically invisible. I have met people who spend all of their time programming, running C++ programs that claims that C++ just isn't there and isn't used anymore. The classical example I found at the Data Sciences Institute at Berkeley, where one of the developers said, well, you know, I use 98% of my time writing Python, and through that, my computer spends 98.5% of its time running C++, because, well, TensorFlow is a C++ library that's used from all the other languages. So I wish it was more visible sometimes, but really solid foundational stuff should be invisible. And so, well, there is a lot of stuff that is based on C++. So C++ was meant to evolve. That is, I knew that no language was perfect for everything and everybody, and that includes C++, of course. The world changes. So when a language reaches some degree of perfection, the world will change, we will change, and we need to make new improvements. The language has to grow the way natural languages grow to meet new things. So here's a very simple example how we wrote a for loop. This was a for loop in C when I started out with it in 79. So we put the loop variable inside to get rid of some verbosity and get rid of some scope errors. And then we got the range for, like in many other languages. And then finally, here's sort of the generalization for parallel and vectorized looping. And of course, the for each algorithm can be changed with some other algorithm if that's what you need. So this is for simple loops, and this is for more complex stuff. We don't just want to be simple. We want simple things to be simple and more complex things to be expressible without overhead or too much trouble. And so all good engineering relies on feedback. So we evolve when we have to, but the design decisions must be guided by real world use and also by ideals. So a general purpose programming language, as C++ is and is meant to be, has to balance a lot of uses. It's not like an academic exercise where you can be the best at one thing and that's it. You have to be good enough at everything that matters to the potential users and the real users. And so there are so many concerns that has to be balanced that you can't list them all. There's a list there. I used an illustration here. Somebody was trying to make that point about airplane design. That is, if you optimize for a single thing, you get something that is basically useless because you have to be good enough at everything. And so there's a list of things that is really important. And some design tensions are inherent. That is, every successful language will face the problems of evolution versus stability. And stability over decades is a feature. It's a major important feature which the average student or the average enthusiast doesn't seem to quite appreciate. C++ C++ programs that are 10, 20 years old can still run and do. And that gives people the confidence to write in a language like C++ because it's very likely that in 20 or 10 years, it'll still run the code they write today. And so we have to serve a wide variety of application areas and a wide variety of people, including novices and seasoned experts. And a lot of tension there because, well, the novices want it simple and the seasoned experts want it the way they are used to, and want advanced features that they can use for doing advanced stuff. One question that I sometimes get is, why do you continue to evolve? Why don't you just stop? I mean, C++ is good enough, so why? And if you want to get something new, get a new language. Well, novelty and simplicity is attractive, but languages tend to grow and get more complicated as they get mature. Typical example is Java, that tripled in size in the first about 10 years. Also, if you look at a new language, it takes significant time for it to be mature, to be used for serious applications, and for broadening the uses from the understanding and interest of the original designers, and also to develop an industrial tool chain. It usually takes about 10 years, it seems. And so C++ is a good solution to a lot of problems. Also, there's hundreds of billions of lines of working C++ code out there. It'll just not go away and shouldn't. And there are millions of C++ programmers that carry knowledge in their heads. You can't just simply upgrade that to something else. So we have to handle the complexity that comes from evolution, from growth. And so to successfully evolve, C++ must be stable, and it has to be viable. It can't just take 5 years out to produce something that is really much better. And you have to have ideals, otherwise it's unguided. Unguided growth is very dangerous in this field. So there has to be ideals. And C++ is one of the ways we try to maintain stability is through an ISO standards committee. And there's a photograph of the committee celebrating the C++ 20 standard. And you can imagine one of the problems about maintaining direction, about stability and such, is that to get something significantly done, a group of people that large has to agree. And, well, you know, programmers and such, it's not easy to get them to agree on everything. So it's hard work, but so far it has worked. And C++ is complicated based on the wide range of uses and based on the longevity of the language. And so one of the things I hear maybe every 2 weeks or so is somebody comes up to me and says, well, you must simplify C++. It's too complex. And while you're at it, please add these 2 new features. They're absolutely essential. You must add those features. Oh yeah, and whatever you do, don't break my code. I've got a few million lines of it. This, of course, is impossible. You have to somehow get out of this dilemma or trilemma, however you want to pronounce it, and so maintaining stability. And we also have to keep simple tasks simple, is the first strategy. Instead of exposing everybody to all of the complexity, we want to be able to do simple things simply, and then when we learn more, when we have more needs, go to more complex solutions. So here's a simple example. I want to sort a vector of integers, sort a vector of strings. The sort function that's generated from a template will figure out that there's a difference between an integer and a string and sort them appropriately. And if we want something more complicated, we can start adding sorting criteria as appropriate if that's what we want. And so there's this gradual thing, keep simple things simple, and make sure that you can do more complicated things well also. And so this can be done. Alternatives for simple users when we learn to do something specific better, like in the for statement. And simplifying generalizations are wonderful when they work. The generalization of sorting that sorts things of a variety of types and data structures is great. And then if something is too error-prone or too slow, we can provide an alternative. And here's a little example. I want to ask if that date here is a Friday. And current in C++ 20, it will figure out which date this is and whether it's a weekday at compile time. This is powerful enough to compute that from that notation at compile time. Decide it is Friday and get on with it. This is blindingly fast, meaning that there is no test here. Okay, so good C++ code is tunable. We provide, if we can, a simple, safe, and general interface to the users. And then if we need to optimize, if we need to be more specialized, if we want to take advantage of things that are not generally known, we should be able to tune. That's the way we get a lot of performance while still maintaining a good interface, safe interface, easy to use interface. A lot of people program the other way around. They expose all the details from their current implementation, and then they're stuck with their initial idea. I refer to this idea of going down through levels of abstraction. You start at the beginning. If you want more control, if you want more features, you peel off a layer of the onion. And if you want to go further, you peel off another layer, and finally you get to the hardware. The reason I refer to this as the onion principle is that each time you peel off a layer, you cry more, because you have to write more code and you have more opportunities to make mistakes. But this way of organizing systems seems to work. And complete type safety is the ideal, static type safety. And with type-rich programming, you want the type system that's strict and flexible for all of the obvious reasons. And we are basically close to there. And type safety is not everything, of course. There's correctness, safety, and performance. There's system properties, not type system properties. And you can write a perfectly type-safe program that has serious logic errors. In particular, I could taste a binary condition and get it backwards the other way. And so to simplify our use, to use all of this stuff, we need guidelines. And I've been working together with friends, colleagues, and many others on the C++ core guidelines, which is trying to say, how do you actually do this in practice? And we are beginning to get support from static analyzers. So here I write a piece of code. And this is not good code. Here I have a pointer to something on the free store, on the heap, on the dynamic memory. And that I leak that one. And there's no problem with this, there's no problem with that. And the static analyzer simply calculates what is correct and do it. So we rely on local static analysis. As I said, this was the C++ core guidelines. And using those, you can reach the aims from the earlier days: no resource leaks, no memory corruption, no garbage collector, because we don't generate any garbage. It is not a restriction of what you can say in the language, and there's no performance degradation compared to modern C++. And this is achievable through sort of a cocktail of techniques. There's the core guidelines, there's libraries, and static analysis. And one thing to remember is not to get overly excited about programming languages and programming techniques. Those are important, but they're only part of our tool chain. And you have to have tool chain or tool change to support a technical community. Now, the first statement in my first book, the C++ programming language, was C++ is a general-purpose programming language designed to make programming more enjoyable for the serious programmer. Now, my editors tried to remove that one 3 times because they thought I had to say something about productivity, reliability, all kinds of language technical things. But really, the language is a tool. And by serious programmer, I meant people who build systems for the use of others. And so we have to remember that there's always people in the loop. And if we forget that, and forget that people are who writes the systems, who use the systems, then we'll produce something that is not particularly useful. And so I have a summary here of the foundations of C++. There's a static type system with equal support for built-in types and user-defined types. Remember my problems with Singular and C. Value and reference semantics. Value semantics is ideal, like in some of the functional languages, but reference semantics is usually key to implementing abstractions that provide value semantics. Systematic and general resource management, usually known as RAII, resource acquisition is initialization, which is not a very good name, but that was the best I could do when I was busy at the time. Support for efficient object-oriented programming. Well, object-oriented programming means sort of the classical way of defining new types of type hierarchies. Flexible and efficient generic programming. What we saw with vectors, those parameterized with types, and then algorithms like sort that is parameterized by parameterized types and by actions that are done with it. Support for compile time programming. We do a lot of that these days. If you can compute the answer at compile time, it's faster than trying to compute it at runtime. And it's amazing how much can actually be computed at compile time. A lot of things turns out to be just having the answer in the generated code. We have not forgotten the C++ origins as a systems programming language. We have to have direct use of machine or operating systems, and we're getting better at that still. And concurrency support is through the library so that we can have a variety of concurrency models and using a variety of hardware with different concurrency features. And so I think C++'s ideals are attainable in the real world, and it's often attained. We can get our performance, reliability, maintainability while evolving, and we have to have interoperability between systems and languages. C++ is not the only language that people use. I've never seen a huge system that was written in exactly one language. I mean, when I started, I was assuming that the system would contain C++, C, Fortran, simpler, and a scripting language, the Unix shell. And developer productivity matters a lot. And so I encourage people not to get stuck in the 1980s. I still meet C++ programmers that hasn't quite noticed that the world has moved on, and we can now do much better than when they learned it a few years ago. And I meet a lot of people who discuss C++ as if it was still the 1980s. So there's language features, there's techniques, and there's tools and libraries. Scaling these kind of things, not easy, takes time. When you have to get ideas through to millions of programmers, that takes time. And so I will end with just adding a list of references that you can use if you get hold of the slides, which I hope you will be able to. Thank you very much, and there will be a Q&A later.